Chapter 8, Section 3 is on graphing logarithmic functions. Now, logarithms are the inverses of exponentials, and as such, they're functions. Each input goes to exactly one output, which means that we can graph them, which I'm sure is an exciting prospect for all of us. So I'm just going to make a table and start by graphing y equals 2 to the x, the exponential function. I'll go from 0 to 3 and negative 3. I'll do this real quickly because we've done this lots of times. 2 to the 0 is 1, 2 to the 1 is 2, 4, 8. This would be a half, a quarter, and a 16th. And I'll just 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Plot these real quick. Here's this asymptote that we've seen before. The graph is growing exponentially, has a y-intercept at the point 0, 1. Beautiful. This is an exponential growth function. Well, log base 2 of x is the inverse of 2 to the x. And so before I graph this by plugging in the points, I just want to show what happens if you just flip the points. To make an inverse, you switch x and y, and you solve for y. So like here's the original function. If I wanted to find its inverse, I would switch x and y, and then solve for y. Well, solving for y means you get the y by itself. The way we do that is we can convert. If I can convert this from exponential form to log form, it's log base 2 of x equals y, which is what this is. Y equals log base 2 of x. But I can also just switch x and y on the points. This goes now negative 3, negative 2, negative 1, 0, 1, 2, 3. And I have 1, 2, 4, 8, a half, a quarter, and a 16th. I just switch the points x and y. Well, 1/16 negative 3 is going to be about here. 1/4 negative 2 is going to be about here. A half negative 1 here. This is the point 1, 0, then the point 2, 1, and the point 4, 2, and 8, 3. This is the logarithmic function. This has a vertical asymptote at the line x equals 0, as opposed to a horizontal asymptote at the line y equals 0. And of course, it's a reflection over the line y equals x, because inverses are those reflections. So this blue curve here is how all of these exponential graphs are going to look at some form. The general form of a logarithm is a times log base b of x to the minus h plus k. A is your vertical dilation and reflects over the x-axis if a is less than 0. If a is negative, b is the base, h is the horizontal translation, k is the vertical translation, and there's an asymptote, a vertical asymptote at x equals h. So I'm going to graph this function over here as an example. Right now the a value is negative 2. The base, calling it b can be a little bit odd later on, but it's the base. The base is 3. The h value is positive 1. And the k value is 0. Well, that means there's going to be a vertical asymptote at the line x equals 1. So I'm going to give this graph a lot of space to go to the right, because these vertical graphs tend to just jump off to the right. That x-axis is a little bit low, but I can live with it. Lots of space to go to the right. And let's go ahead and label this. I've not been great about labeling all my graphs, and I should be. We'll count by 1s everywhere. Now this isn't going to be able to go negative because of this asymptote, so I don't need to label anything over on this side. Nothing's going to move that direction. It's all going to be going to the right. What I'm going to do now is plug in what I call smart points. This is one of the ways you'll see me do a lot of this graphing, by plugging in smart points. I want to take this and have this x minus 1 come out to things that are powers of 3. I want x minus 1 to come out to like 3 to the negative 1, 3 to the 0, 3 to the 1, 3 to the 2. The idea here is I'm going to at some point be doing the conversion. 3 to something equals the number inside the input here. I want 3 to some power to come out to those numbers. So I want this x minus 1 to equal numbers like 9 and 3 and 1, because those are all powers of 3, or a third. So if I want x minus 1 to equal 1/3, then I really want x to equal 4/3. What I did is I added 1 to both sides. Right, what I'm saying is if I want x minus 1, I'm going to look at this line here. If I want x minus 1 to equal 1, then I would add a 1 to both sides, and I really want x to equal 2. I'd plug that in for x. If I want x minus 1 to equal 3, then x should be 4. And if I want x minus 1 to equal 9, then x should be 10. These are the points I'm going to plug in for x in my table. Now I've got to go and evaluate to see what I get out for y when I plug these numbers in for x. So, let's start with 10. This will be, I think, one of the simpler ones. I'm going to plug a 10 in for x. That means I'm doing negative 2 times the log base 3 of 10 minus 1. Well, 10 minus 1 is 9, which is very nice, because the log base 3 of 9, we can easily calculate. This is asking the question 3 to what power equals 9, and that power is 2. So it's negative 2 times 2, which is negative 4. I get at the point 10, negative 4, which is here. Let's plug in 4. If I plug in 4 for x, well, I'm doing 4 minus 1, which is 3. So I'll write this down here, negative 2 times the log base 3 of 4 minus 1. Well, 4 minus 1 is 3. Log base 3 of 3 is 1. And negative 2 times 1 is negative 2. This is the point for negative 2. I plug in 2. 2 minus 1 is 1. I'm going to come up to this spot now. So it's negative 2 times the log base 3 of 2 minus 1, which is negative 2 times the log of 1. The log of 1 is 0 because 3 to the 0 power is 1, so it's negative 2 times 0, which is 0. And at this point, I'm just going to take this pattern and moving up to, this is going to be up to also. So I had the point 2, 0. And the point 4/3, 2. This graph is going like this. It was reflected because of this negative. Okay, so the previous graph went up like this, had this curve to it. But now this was reflected, so it's all going the opposite direction, and it was moved to the right 1 by those values. Now, there's a lot of information on this page. I'm going to do another example of graphing like this, which is, I think, a pretty mentally taxing way, but a pretty effective way to do it. I'm actually going to show you 3 different ways to graph logarithmic functions. I recommend you work to understand and become proficient in all 3 of them, but just master one of them. What we just did was graphing by plugging in smart points, which is a mentally heavy, mental math heavy way of doing it. I'll also show graphing by transformations to the parent function, which is time intensive, and graphing by converting to an exponential form, which is algebra heavy. I think this one is the least brain intensive. This is probably the one that people do the least, but every class there's always 1 or 2 students that prefer it this way. So here's another example of graphing by plugging in smart points. I'm going to pick numbers to plug in for x that are going to come out clean as I try and graph this. Again, I'm moving the x and y axis way far to the left because I don't worry about negative numbers. This isn't going to be able to go negative. I'm going to look at the function 3 times log base 2 of x minus 4 and think, I know that I want to end up doing 2 to some power equals the thing in here. All right, that's going to be the critical step to all of this. Well, to make this easy, I want the thing in here, I want this x minus 4 to become powers of 2. If I can make x minus 4 equal the powers of 2, which are like 2 to the 0, 2 to the first, 2 to the second, even 2 to the negative 1. If I can make x minus 4 come out to those values, which are a half, 1, 2, and 4, the computations get a lot simpler. The graphing will be with really clean whole number points. So I want x minus 4 to equal a half, and I want x minus 4 to equal 1, 2, and 4, and I'll probably even do 8. This should be a minus, not an equals. Well, to make this happen, I just add 4 to everything. So I'm going to have x equal 4.5, x equal 5, x equals 6, x equal 8, and I can even do x equals 12, because I know that 8 is a power of 2 also. I'm going to plug those numbers into a table. And that might feel like a decent amount of work to just get stuff to plug into a table. I still have to do all of my, evaluating and graphing now. But when I plug these numbers in for x, the evaluation gets a lot simpler. Like I'll start with 12. I think the bigger numbers are usually the easiest. 12 minus 4 is 8. Log base 2 of 8 is 3, because 2 to the third power equals 8. 3 times 3 is 9. So I'll actually kind of work that out. I won't work them all out in this much detail, because the goal is, if you can do it this way, you can hopefully start doing this mentally more and more. I'm doing log base 2 of 8. Well, for this, the question is 2 to what power equals 8, and that's 3, and 3 times 3 is 9. We plug in 8. 8 minus 4 is 4. Log base 2 of 4 is 2. 2 times 3 is 6. And this number here will be the change along this y side of the graph. So if I picked these points correctly, these can actually just start counting by 3s. So I have 4.5, negative 3. I have 5, 0, 6, 3, 8, 6. Then 12, 9. 7, 8, 9, 10, 11, 12, 7, 8, 9 would be about here. This graph has a vertical asymptote at 4 and curves off like that. The domain is x is greater than 4. The range is all real numbers. This next method is the one that I actually find the most cumbersome and confusing, but I think there's always students each year that like doing it this way. And so I show it. It can be nice because it just is very visual in how it's presented and how it's accomplished, and that can be really appealing to a lot of people. I'm going to take the parent function and then manipulate it. So the parent function is just log base 3 of x. From there, I'm going to reflect it, vertically stretch it by 2, move it left 1, and move it up 4, and I'll do it in that order. Okay, those are the transformations, and the order really matters, so I'll do it in that order. And I'm going to show that both on a table and on the graph. So the original parent function would graph like this. I would plug in the numbers 1, 3, and 9, and a third, and get negative 1, 0, 1, 2. So it's a third, negative 1, 1, 0, 3, 1, and 9, 2. Graph does this. Now what I'm going to do is translate and dilate and reflect and move around this graph. So this affects the x value. The x values of my new function, which is negative 2 log base 3 of x plus 1 plus 4, the x values all get smaller by 1. They all move left 1. So this becomes negative 2 thirds, 0, 2, and 8. The y values are all going to get multiplied by negative 2 and then have 4 added to them. So negative 1 times negative 2 is 2 plus 4 is 6. 0 times negative 2 is 0 plus 4 is 4. 1 times negative 2 is negative 2 plus 4 is 2. And then 8 becomes 0 because these are all going down by 2. And they're all going down by 2 because that's negative 2. I'm going to hide this now. So I plot those points. We have negative 2 thirds 6, which is going to be about here, 0, 4, 2, 2, 8, 0. This has a vertical asymptote at -1, so the graph is here. And there is our graph. Now, forming the parent function can be quite simple. This moves things left to right, this moves things up, down, this multiplies the y value. Okay, the last method that we have here is by converting into exponential form. So remember that, like, if we have b to the x equals a, it's the exponential form. The log form is log base b of a equals x. So this is given to us in log form. We can convert it into exponential form, and that makes the plugging in of points easier. It also ends up being the same amount of work, just some people prefer having it switched forms. So to convert to log form, I have to get this log by itself, which right now just says og. So what I need to do is first get rid of the 4 multiplier and the 2 subtractor on the end. So I'm going to start by adding a 2 to both sides, which gets me y plus 2 equals 4 times the log of 1/3 to the x. Then I'm going to divide everything by 4. So y plus 2 divided by 4 equals log base 1/3 of x. And now that I have the logarithm part all by itself, I can convert. So I'm going to do the base to this power equals x. So it's 1/3 to the y plus 2 divided by 4 equals x. And then the sort of nutty thing about this process is now I'm going to plug in numbers for y instead of for x, because I got the y by itself. It's like the y is now my independent variable or my input. And I still want to be plugging in smart numbers. I still want to plug in numbers for y that will make this come out cleanly. So I'll do 2, because 2 plus 2 is 4, and 4 divided by 4 is 1. And I'll do 6, because 6 plus 2 is 8, and 8 divided by 4 is 2. I'm going to plug in all of these numbers that, when I add 2 and divide by 4, get me whole numbers. So let's start with -6. If I plug in -6, -6 plus 2 is -4. -4 divided by 4 is -1. 1/3 to the -1 is 3. This is -6, 3. Let's plug in, or 3, -6 is the actual point. I'm going to graph the point 3, -6. We plug in -2. -2 plus 2 is 0. 0 divided by 4 is 0. 1/3 to the 0 is 1. We plug in 2. 2 plus 2 is 4. 4 divided by 4 is 1. 1/3 to the first is a third. 6. 6 plus 2 is 8. 8 divided by 4 is 2. A third to the second is a ninth. This is going to be a 27th. And I can't really graph that very accurately. I think I'm going to go to -10. I'm going to go up 4 more this direction. So I plug in a -10 for x. -10 plus 2 is -8. -8 divided by 4 is -2. 1/3 to the -2 is 9. So these are the points I want to graph. I'm going to go from basically 0 to 9 on the x's, which is why, again, I pull the y or the x-axis way over here. My y's are going from -6 to 10, so I'll just put that in the middle-ish. I get that line's not perfectly horizontal, but I'm sure you can live with it. So then I have the point 3, -6. I have the point 1, -2. 1/3, 2. 1/9, 6. And also had 9, -10. 6, 7, 8, 9, 10, about here-ish. So remembering this graph has a vertical asymptote, then it zooms off to the right. Domain, x is greater than 0, range, all real numbers, vertical asymptote at x equals 0. Logarithms have vertical asymptotes at x equals h. They can be graphed in 3 ways, be proficient in all 3, but master one of them. Plugging in smart points, graphing via transformations, and converting into log form, and you can't always trust your calculator. Nice work, everybody.